Here's sample test problem number 6. The free fall acceleration on the moon is 1.67 meters per second squared. What length pendulum has a period of 1 second on the Earth? Good question. In general, for all these simple harmonic motion problems, we're interested in the angular frequency, and for a pendulum problem, that is g over the length of the pendulum. And hence the period, which is 2 pi over the angular frequency, is going to be 2 pi times the square root of the length over g. So if we were to solve this for the length, square both sides. So it looks like this. And then L would equal g times the period squared divided by 4 pi squared. That would be the length of the pendulum as related to the period. So the length that we're looking for in this case is going to be on Earth 9.8 times a period of 1 second squared over 4 pi squared. And that's equal to 0.248 meters. So that's the length of pendulum on Earth that would have a period of 1 second. If we were on the moon, what would be the length of the pendulum? The length of the pendulum on the moon is the gravitational acceleration of the moon times the period squared over 4 pi squared. So on the moon, that's going to be 1.67 meters per second squared times 1 second squared over 4 pi squared. And that's equal to 0.0423 meters, or 4.23 centimeters. So one length on the Earth is about 1/4 of a meter. The other length is only 4.23 centimeters on the moon, because the moon's gravity is so much weaker and it's not going to pull it down as fast. Part C. Find the mass suspended from the spring that would give an oscillating period of 1 second with a spring constant of 10 newtons per meter. So in this case, omega is the square root of k over m, and hence k is going to equal m times omega squared. So the period, again, is 2 pi over omega, which is going to be 2 pi times the square root of m over k. Square both sides. So period squared is equal to 4 pi squared m over k. And hence, mass is going to equal k times the period squared over 4 pi squared. That's going to be 10 times 1 second squared over 4 pi squared. And that is equal to 0.253 kilograms. I think one point of this part C is that we could have this mass anywhere, because it doesn't depend on gravity g, and it would have the same period of oscillation, whereas for our pendulum it depends on the gravitational field that we happen to be in. So as a timekeeping device, the spring mass spring system is a much better thing to use, because it can work anywhere.